And here we go. I don't know what happened, but you can use trigonometric substitution.
Are we recording?
Yes,
Hi.
we are recording.
Hello.
Hi, Jake. I'm Peter.
Hello, Jake and Peter.
Hello. This is your computer.
This is our computer.
You can use trigonometric substitution if any of your integrals involve a radical that looks like this. Radical a squared minus u squared, radical a squared plus u squared, or radical u squared minus a squared. Okay, make sure that you know your Pythagorean identities. These are the three versions. Hopefully you don't have to write these down, but you can if you need that visual. What I'm saying is I'm hoping you know them. Okay.
You just have, I remember the first one, and then I have to divide.
Yeah.
Yeah.
That's okay. There's nothing wrong with having to divide as long as you know how to get there. Okay. But you're going to use these three often. So you're trying to take a picture?
Yeah, because I know.
I can come back to the side of the so basically, okay, so if we have 1 over 16 plus x squared, we know that that's our cosine, right? But if we have like x over 16 plus x squared, okay, we can use substitution, right? But we could also use trig substitution, okay? The problem that you guys did the other day, where not half of you, but a good handful of you forgot to divide out the improper fraction, that would be one that we can now use substitution on instead of having to divide. Excuse me, trig substitution. Okay. So anything that has these in the integral, we can use trig substitution with. So, for integrals involving square root of a squared minus u squared, let u equals a sine theta. Don't feel like you need to draw the triangle right now, but know that we will draw a triangle every time we do a trig substitution, so we can reference when we go back in to write everything back in terms of x. But what you need is that if you have square root of a squared minus u squared, you're going to use a sine theta. Integrals involving, okay, sorry, maybe I should tell you why. That's what I was waiting for you to write it down. Okay? What's going to happen is you're going to have a squared minus a squared sine squared. And what you're going to be able to do is factor out an a squared. And what do we know about 1 minus sine squared? It's cosine squared. Okay, you don't necessarily need to write that down because you're going to be doing it over and over and over again in our problems. But now we have a cosine theta. Woohoo! And we can move forward. Okay. If we have this, we're going to let u equals a tangent theta. Okay, what trig identity what's going to happen underneath the radical? You're going to get a squared plus a squared tangent squared, right? So you're going to be able to use that 1 plus tangent squared as secant squared. And last but not least, if you have u squared minus a squared under a radical, you're going to use a secant theta. All right, you ready? Write this down.
It doesn't seem small.
Do we know what the same side derivative is?
No.
It's a squared minus.
Well, okay.
We already know.
So, since we have a squared minus u squared, okay, but instead of u we have x, we are going to let x equal a sine theta. So since this is 16, we consider that to be 4 squared minus x squared. So x is going to be 4 sine theta, which means dx is 4 cosine theta d theta. Just like u substitution, we can only make substitutions based on what we have in the integral. But this is where it's nice. In u substitution, we like make patterns fit, right? Where here, our dx is just a straight up substitution. All right? So, what do we have? Well, we have 1 over 16 minus our x squared becomes 4 sine theta, the quantity squared. And our dx becomes 4 cosine theta d theta. Okay, this is kind of, it hurts my eyes to look at a little bit. Okay, let's make it look a little bit nicer. So we have 4 cosine theta in our numerator, and in our denominator we have the square root of 16 minus 16 sine squared theta. D theta. Okay. All right, so I'm going to save some room. We like to save some room, right? What can we do with this right here? We can factor out of 16.
Yes.
Are you guys all okay with me doing that?
Yeah.
Alex, what happens? You can make it into cosine squared. Oops, that's so in our denominator we have radical 16 cosine squared. And what is the square root of 16 cosine squared?
4 cosine theta. Oh my gosh. So it's theta.
What? It's just what? But Isaac, what's the antiderivative of 1 d theta? There it is. But hold on. Why not?
You gotta put it back in.
Put it back in terms of x. So our original integral was dx, which means our answer better have an x in it.
Get better.
So what is theta?
And it's,
It's
1/4 anti-sine
If we solve for theta, we have x over 4 equals sine of theta. So I'm going to let you try that again.
inverse.
So the inverse sine of x over 4 would equal theta. Which means our antiderivative is theta. Inverse sine of x over 4 plus c. Remember way back in the beginning where I said, hey, you should know this antiderivative?
I don't remember that or the antiderivative.
Ha, ha. Okay, so on the quiz Wednesday, you could have done this problem without trig substitution. Okay, now trig substitution is a little bit of work. It's going to be helpful to remember that antiderivative, but if you don't, hey, guess what? You have a backup method. I wanted to start with this easy example because we were supposed to know the answers to it. Okay, now we kind of forgot. Not a problem, we have this backup method. Okay.
Oh,
Is inverse sine the same as arcsine?
Yes.
What's the thing?
Same thing.
Okay.
Same thing. It's just different notation. All right, let's try something else.
Oh no. That's in the
Are
number.
you kidding me? So you got x minus 2 on top.
Julia? No. Good answer. Okay, so we have square root of x squared minus 2 squared, which means we can let x equal 2 secant theta. If it's x squared minus 2 squared, or a squared, whatever. Okay. Which means dx is 2 secant theta tangent theta, d theta. What's ridiculous?
No. Don't even.
Code word champion.
Vietnamese Olympic champion.
I go like.
Code word.
What?
Already on there.
I don't know if you talk loud enough from way over there.
No, you can hear him.
You can?
Yeah.
That's good to know.
NJ.
Okay, so I have replaced my x's. Then we have to replace dx with dx.
Like, I feel sorry.
Well, trig is a very, very helpful, like just basic sine, cosine, tangent. I can't tell you how helpful they are throughout. Ever since you've learned them, you've been able to use them in different capacities. Okay, so let's at least take into consideration that we can cancel there. That's one less thing to worry about. Let's talk about what's underneath the radical. Underneath the radical, we have 4 secant squared theta minus 4. Oh, we no longer have a numerator. My apologies. Times tangent theta. Okay. What can we do underneath the radical? We can factor out a 4. And what do we know about secant squared minus 1? So we have the square root of 4 tangent squared times tangent. Okay? So what we are working with is the integral of 2 tangent squared theta d theta. Well, I'll tell you what. It is a good thing that we just came off a section of working with trig integrals because we have a tangent squared to take the antiderivative of. Can we take the antiderivative of tangent squared?
No.
No. But what could we change it to?
We're going back to secant now?
I'm gonna do like one of these. And then
What? Okay, so this is not quite as painful anymore. What's the antiderivative of secant squared? Okay, now here is where we're going to need to draw the triangle. Okay, so you don't want to like solve for theta and plug it into tangent theta. No.
what happens tangent of whatever it was?
No.
If you do like tangent of
Right triangle, you have a theta. What do you know about theta? Well, we know that x over 2 equals the secant of theta. Do you agree?
yeah.
Okay, so our secant ratio is x over 2, which means hypotenuse over adjacent is x over 2. And the Pythagorean theorem would tell us that the other leg would be the square root of, conveniently, x squared minus 4. So in our answer, when we have tangent theta, what is the tangent ratio of theta? Try that again. X squared minus 4 over 2. Square root, right? So the tangent ratio, square root of x squared minus 4 over 2. We'll just replace it with that ratio. Any trig function you have in terms of theta, you need to replace. Okay? What was theta? Arc secant of x over 2, correct? Plus c. So if you want to make it a little bit prettier, you can distribute that 2 through, and then there's no longer a fraction. But that is trig substitution. Okay. So in the first example, we didn't need to draw a triangle because we were only left with theta. But if you have any trig function in your final answer, you're going to need that right triangle so you can figure out the ratio to substitute back in. One more example. Yes, you need to know how to do this one. What's different about it?
It looks like a secant.
Okay, well the x is out front, and that's what makes this method nice, is that it's not scary. So we have that 4x squared. So we need to view that as like 2x the quantity squared plus 3 squared. So instead of x equaling, well, which trig function do we need to use for this substitution?
Tangent?
Tangent. Instead of x equals a tangent theta, we need 2x equals 3 tangent theta. And since we're going to have to replace x's and dx, you should probably go ahead and rearrange it so that x is 3/2 tangent theta, so that you can get your dx by itself. So I'm going to go ahead and draw my triangle now. If we put the tangent of theta by itself, the tangent ratio would be what? Tangent of theta would equal 2x over 3. So opposite over adjacent would need to be 2x over 3. See how I get those labels? Pythagorean theorem really is just going to be whatever we have in there. Okay. Now, what I want to tell you about this, these substitutions. So when I originally talked about the tangent substitution, like we have it in the radical. What we're going to talk about Monday is this doesn't even have to be in the radical for us to use it. This could be 4x squared plus 9 to the 3/2 power, and we can still use it. Okay, and we'll look at more of that kind of stuff on Monday. But let's do this. So we have the integral of 1 over x times the square root of 4x squared, which really is just going to become 9 tangent squared theta. Okay, let's talk about how I got that. 4x squared is the same thing as 2x the quantity squared. If 2x is 3 tangent theta, then 2x the quantity squared is 3 tangent theta squared. So I just wrote 9 tangent squared. I'm trying to save us some room. Is that okay?
Oh.
All right. And dx we're going to replace with 3/2 secant squared theta d theta. Hey, the 3/2 can cancel. And what are we going to do here? We're going to factor out a 9. And you're going to do this enough to where you're going to be able to kind of like see what's going to happen, right? What is tangent squared plus 1? Just positive secant squared. So this becomes 9 secant squared. So if we apply the radical, 3 secant. So I'm going to take this 1/3 out front. If we reduce that down we have secant over tangent, right? And secant over tangent kind of running out of time, so I'm just going to tell you it reduces down to 1 over sine, which we can change to cosecant. Is that okay if I tell you that?
Yep, take it.
Okay, this is one of those you have to look up on the chart at the front of our chapter. The antiderivative to cosecant is negative the natural log of cosecant theta plus cotangent theta. So if we look at our triangle, we need our cosecant ratio. Cosecant is hypotenuse over opposite. So hypotenuse over opposite. Plus cotangent. Our cotangent ratio is adjacent over opposite. Okay. You need to do some homework this weekend. We are going to work on this more on Monday, but we're going to look at some more complicated examples. So I need you to be able to do the basic problems.
Basic, huh?
Basic problems.
PH 14.